Hi, everybody. My name is Charlie Savage, and I'm with Privateer/Orbital Insight. And I was going to talk about how we use CNG technologies in our geospatial platform, which is called Terrascope. So Terrascope has grown so Orbital was founded 12 years ago, and I've been at Orbital for about 3.5 years. I'm the chief architect, and what I came on to do was basically build Terrascope. And Terrascope is based on the learnings from the previous platform, which was called Go, which was based on learnings before that. So with Terrascope, we wanted to make it easier to combine imagery and geolocation data, make it easy to add new data sources, make it easy to add new algorithms and models, and then one thing that's actually turned out to be quite important is deploy anywhere, so cloud, in government cloud, on-premise, on bare metal, and in air-gapped environments. And so as this move from Go to Terrascope, we've adopted, and I'll go through these various CNG technologies. And let me just show you one quick use case so you kind of see what we're trying to accomplish. So one thing we work on is marine domain awareness. And so this gets a lot of press these days. You'll see stories in the New York Times and other mainstream media. And what happens is you have hundreds of thousands of ships. They're going around the ocean. And in this screenshot, that blue track is a ship. And that blue track is coming from AIS data. So as a ship sails around, it's supposed to send out pings periodically. Those are called AIS pings. Ships will, though, do things like turn them off. So the blue track is from AIS data. It also can be from radio frequency data, which is satellites that hear emissions that come from a ship, like if someone's using a satellite phone. And in this case, the ship starts off near Vietnam, goes around Malaysia, gets into the Indian Ocean. At the Indian Ocean, that green triangle it's actually changed its ID. So from one ID to another ID, probably because it wants to do something that's not so great. And then it turns off its AIS data feed. And so at that point, we have algorithms that try to predict, using a bunch of different ways, of where the ship's going to go. We also keep track of every satellite and every constellation, so we can go, okay, we have the ship, it went dark. We now want to see if we can acquire it using a satellite imagery. Okay, it looks like, in this case, Planet has satellites in that area. We'll then try to task through Planet. And if we get super lucky, you end up with this one on the left where our ship, that we found the ship and it's docking with another ship, which is generally, and it doesn't want to know that that is happening. So usually it's like it could be an illegal fishing boat that's going to a mothership to drop the fish off. It could be, a Russian oil tanker that's trying to evade sanctions. It could be all sorts of things. So the point of Terrascope is to enable things like this. So it's a combination of geolocation data and satellite imagery, both EO imagery, optical imagery, as well as SAR data. So, and here's a second quick use case. This is a map that's showing GPS interference. So various state actors will interfere with GPS signals, which affect the navigational quality of data that airplanes and ships get. In this case, this is the world up in hexes, where red is where there's more interference, and green is where there's no interference. So let's get to the CNG technologies. So what do we use? So for discovery, we use Stack and the SQL 2 query language. For imagery, we use COGS, so Cloud Optimized GeoTIFFs. We make heavy use of OGC Tiles API, the newer versions from like 2019, 2020. And on geolocation, we use Hive partitioning, which will move to Iceberg, GeoParquet, with geo-arrow encoding of geometries, and then OGC Feature API, but we use that with GeoParquet. So in Go, so remember Go, second generation, Terrascope's third. So in Go, we had an image catalog. And what that is a custom implementation, because back in the day, 5-8 years ago, you talk to provider APIs. They're all different. And when you try to build a software product, you need a unified API. So we created our own catalog, created our own API, and then providers were limited. Like, you could not dynamically talk to Planet or to Maxar or to whoever it was at the time, or Airbus. You get rate limited, so you couldn't do dynamic searches of what satellite imagery is available. And the APIs were too slow, and they couldn't handle complex geometries. So if I want to do an island, or if I want to do a country. And so what we did is we built our own catalog, but it didn't integrate with geolocation data sources. And it was all custom, right? And so in Terrascope, we switched to Stack. And so we made this move a couple of years ago. Stack provides that unified API, which is great. And when providers provide Stack catalogs, that's great. That makes our life easier. That's still, unfortunately, not the case across all providers, but it's getting to be that way. And we also want to, this helps us, one of the design goals was to make it easy to bring your own data sources to Terrascope, especially when you're in a high-side environment in the government and they have their own data sources. So if you have a data source which can register itself in Stack and create a new Stack collection, then the rest of the system knows how to search for that data and to find it. So Stack's really a great unifier that way, along with the SQL2 language. And so here's a little picture, what we basically have now, where we have Terrascope at the top. We have these different data sources, Planet, Maxar, ISI, Hawkeye, AIS, et cetera. And these are basically little microservices. They provide the Stack API. We then have our own hosted Stack API, which is everything we've ingested. So we've acquired data, say from Planet. We've ingested it. Now we have it locally in our Stack catalog. And so as a user, sometimes you want to get that ingested data because it's already been purchased. You don't want to purchase it twice. Or you're in an air-gapped environment. You can't reach out. And sometimes you want to search for, OK, well, here's an area. Here's a time. What data have I already ingested? But what data do I want to go see is available? So go talk to Planet's API and see what they have, or talk to Maxar's API. So this is the setup we have now. Here's just a screenshot from Terrascope. This is actually showing data that's coming from, in this case, Hawkeye 360. So for given a particular time and area, here's all the pings that we have from the Hawkeye data set. So what we want to do next on Stack is we want a hierarchical Stack, or maybe recursive or federated Stack, or maybe recursive queries are the best way to talk about it. So we want just one Stack catalog. And in that Stack catalog, we want to have a root catalog, which you always have, but then wouldn't it be good to have a Planet catalog, and then here's our local collection, and then here's a remote collection, which might be Dove, or it might be SkySat, and then Copernicus, et cetera. And the idea would be you could just go to the Stack catalog, and then you could say, OK, I have something here, or if not, let me go search the remote catalog. So you could only have one query interface. So that would be great. And then the other thing is we want to add in geolocation data sources as collections. Every data source should be found in one place. Now, we're not going to go put 10 million AIS pings in a Stack. That doesn't make sense. But we do want to know that we have a collection of AIS pings from this data source, from this provider, for this area, for this time. And then when you want the items, you redirect to an OGC feature API, which is designed to serve that type of data. So something more like this, where you have Terrascope, you have a Stack in the middle, and you have smart enough clients that can go here, and then they search here, or they can code down and then search the particular provider's API. Or like on the right-hand side, where we have Hawkeye and AIS, they'll never, I doubt they'll have a Stack catalog. It's a different sort of data. It's not imagery data. But then you can put in an adapter to go to those catalogs. Or not catalogs, but they have their APIs. So that's how we use Stack. I'm going to move on to imagery. So in Go, we generally actually stored chips. So we instead of a full scene, which are really big, we get chips because users would draw smaller AOIs, and you don't want to buy the whole image. You want to buy this chip. Okay? So we generally have chips, not scenes. Data's all different. Metadata's all different. So we normalize 5 properties: cloud cover, azimuth angle. But that's it. 5 out of hundreds. Sorry. And then for tiles, we have a custom way of doing algorithm tiles. And what I call an algorithm tile is a tile. You take a scene, and you split it up, and you tile it so it can be fed to a CV, a computer vision algorithm. So it's not like a display tile. It's not like you see in a Slippy map. It's a tile specifically designed for computer vision algorithms. And we have our own custom way of doing that. We also have visualization tiles, heat maps, for example, which we would create server-side. And then we didn't really do OGC tiles for Slippy maps. So just here's some visualization tiles. It's kind of what you would expect. Heat map on the lower right, road networks, object detection, so these sorts of things. So that's what a visualization tile would look like. Now, so in the OGC standards, you go farther north, right? Circumference of the Earth gets smaller. And so OGC in the standard keeps the same tile widths, but has less tiles, as you can tell. We did the exact opposite long before that OGC standard exists. We have the same amount of tiles, but we make them smaller. So it's a conformal projection because we want to keep shapes, because that's important for CV algorithms. But so of course the tiles have to get less wide because you're going north. So that's one challenge we have in fitting to the OGC standards. So we have a different way of doing projections and the different way of doing variable tiles. So in Terrascope, first thing is have cogs. So cogs are super helpful. You've heard all about them. But it enables dynamic tiling, which can be pretty helpful in some cases because they're optimized so that you can read certain zoom levels. So switch to cogs. Most providers give us cogs now. When they don't, we make them. And then the OGC tiles API. So instead of having a separate system for visualization tiles and a separate system for algorithm tiles and a separate system for display tiles, and that's kind of what most of you, I think, what we call, the Slippy map tiles, we want one way of having these. And we adopted the OGC tile API for this. So we have tile matrix sets. So given a scene, we'll have up to 3 tile matrix sets, one for each of these or more. And then we link the stack item. It's really important for us to be able to link the stack item to the tile, or the tile to the stack item. And so there's a stack tiles extension, which we don't actually use, because it's pretty verbose. And so we have basically a simplified version of it, but it's the same concept. And then, so that's imagery. So moving on to geolocation, which is an important part of Terrascope. So in Go, we had almost a petabyte of this data. So this data is everything you have, any device, most devices, put out a ping. So a ship puts out a ping, a car puts out a ping, your cell phone pings all the time, and then airplanes send out pings. So you have all this data, and it's pretty simple data in that it's got an X, it's got a Y, it's a location, and then it has any number of attributes depending on who the provider is. And so this is a petabyte of data. And so you have to partition it. And so Iceberg is the new hotness these days. So basically, Orbital did something like Iceberg a long time ago because we had to. There was no choice in the matter. And so when you get this data that's ingested, you partition it, and we tend to partition it by time and by location because they're the two main ways that we query it. And we built custom APIs around that. We built custom tools around it. And because of all this data, that's why we did visualization server-side. It's too much data to send to the client. So one move we made on Terrascope is the quick, easy win for us is to move to Hive partitioning. So we basically have all our same partitioning schemes, but we have Hive partitioning, which basically puts the keys into the paths. So this is kind of the old way. This predates Iceberg. But it enables the use, most tools support it, like PyArrow understands it, DuckDB understands it, Data Fusion understands it. So by moving to Hive partitioning, we now are able to use all these SQL query engines to unlock querying this data, in addition to the tools that we have custom built that we still use. And then at some point, especially now with the adoption of geospatial support into Iceberg and to Parquet, we'll move to that. And in the same way, switch from Parquet to GeoParquet. And we're spending a lot of time on figuring out, okay, what makes sense for GeoParquet. So the number of files you have and the size of those files and the size of the row groups in those files, all these things really matter for your performance. And it depends on what data you have. So we've been spending a lot of time trying to work that out. Because when you're doing, we get data every 10 minutes from some providers, and the data for, sometimes it takes, you get your first data in 10 minutes, but it might take 3 days to get the rest of the data. So you need to deal with, you have data delivered over a few days, you generate thousands of files when you ingest it, but listing thousands of files is terrible on S3, it's too slow, and so you need some sort of compaction scheme, something that Iceberg's dealt with, but all that you need to deal with. And then our results, when you run an algorithm, we just treat the results as another data source. So it means you can kind of stack algorithm on top of algorithm, so you can do one analysis, take that, and use it as the base for your second analysis. So kind of like a DAG, a directed acrylic graph, is how we kind of model the way in which we do analyses. And then so on Terrascope, continuing, so on the geolocation APIs, so one thing that we have put in place now is using the OGC features API with SQL 2. So that gives us a good query language that describes every way that we need to query this geolocation data. But instead of doing GeoJSON, GeoJSON is wonderful and is great, but it's not wonderful and great for 10 million pings. It just doesn't scale. And so instead of that, we're just using GeoParquet. So my reading of the spec is you can return whatever format you want in the OGC feature specification. GeoJSON is the one they give all the examples in. But instead, we'll return GeoParquet. And as part of that, instead of doing a lat and long column now, or poly, or some sort of other representation of geometries, we'll now geo-arrow encode them. And that's important for the next step. And so for some of the great work of the people who were at this conference of getting data from the server to the client quickly, if you can encode your geometries in geo-arrow, then you don't have to deserialize them when you get through the front end, and that makes it a lot faster to render. And so now we can send hundreds of thousands of data points to the UI. And the reason why you want to do that, first it seems kind of dumb, but because you want interactive visualizations. So generating visualization server-side is okay, but what users really want is to have a little slider, and they turn things off, they turn things on, and you have to have the data on the client to do that, and you have to transfer a lot of data to enable that. And so we're kind of going down the path that others at this conference have started, which is we enable these interactive visualizations by setting GeoParquet files, stream them with geo-arrow geometries encoded, and then put them through DeckGL, and now we can enable client-side visualizations. So here's a screenshot of this. This goes back to the navigational quality example I showed with the spoofing. And so each of these colors is a different airplane, basically. And it's showing the pings of where the airplanes have been with their navigational quality indicators. So this is about 750,000 pings over, I don't know, a short amount of time, but which we can get from the server to the client, render this map in a couple seconds, and then users can zoom in or zoom out in different areas, and they can say, well, I want to filter based on a location, I want to filter based on a time, I want to filter based on how degraded the navigational qualities are for that particular flight, et cetera, et cetera, et cetera, whatever attributes the data has. And so then this enables the client-side visualizations. So I went through that really fast. But in summary, when we went from Go to Terrascope, we thought, okay, which CNG technologies made sense to adopt, replacing what had been homegrown, and what things homegrown did we keep? And so what we've taken for the CNG technologies is Stack, that unifies our discovery and searching of data, both imagery data and geolocation data. How do we unify all these tile sets we have? So we'll use the OGC Tiles API for doing that. How do we get data from the client to from the server to the client quickly? GeoParquet, GeoArrow for enabling client-side visualizations. And then using OGC Features API for having a standard API for getting geolocation data from all these different ping sources that we have. And that's my presentation. Any questions?
This is awesome. I think this might be one of the first production uses I've seen of GeoArrow encoding in GeoParquet.
Yeah, well, Kyle inspired us, and we said, is this going to work for us? And we tried it, and lo and behold, it did. So it's been great.
I want to see more of it.
Yeah.
It's often.
Yeah.
But yeah, when you have control over the environment that are doing that,
Yeah.
Like I was thinking about distributing, so I'm like, no other tools read this, but you get one tool.
Yeah, and on that, one quick thing. So this is not released to production, but for this project here, which we're doing for Defense Intelligence Unit, I think I can say that, the new version of this is all going to be based on that. So it's going to be great.
The features API version, is that just a custom home-built implementation of features API?
Yeah.
And what's it?
But behind the scenes, what it's really, well, so we're experimenting with, okay, so we have this partition data, so what's the best way to query it? So we have our own tools, so we test those, and then we test it against DuckDB, and then we've tested, which I really liked, is Data Fusion, which is kind of the Rust implementation of that, and then there's the other one that's from the C++ world, and PyArrow. So we're saying, okay, which one is quickest to get us to the data so that we can then stream it, and then we just have a Python service that pretends to be, implements the API. Yeah, the ODC API. What's the what?
The pin data.
Yep.
What's it stored in behind API?
Oh, it's an S3.
But,
It's been traditionally in Parquet, but we're moving to GeoParquet with the GeoArrow encoded geometries. So basically what we do now is we ingest the data, it's in Parquet, and then we re-ingest, we don't re-ingest it, but we then flip it to GeoParquet for what we're doing now, but we're obviously just going to go right to GeoParquet shortly.
and so you're saying putting the features API
Yeah, we'll still do that. Because it gives you a unified interface. You know, you can use SQL too. So, because on the front end, users always want to query for some, they don't want the whole data, they want some subset of the data. And so we use SQL, so we have a nice little query builder in the front end, type in what you want, that's encoded in SQL 2, goes to this service, then it does the translation to DuckDB or Data Fusion or whatever it is we decide to use. Yep.
Is all that in memory for the SQL queries, or is it mixed?
I mean, memory's, yeah, certainly a lot faster, so it kind of depends. It depends on what query engine you're using. Yeah.
Am I correct in thinking that you're doing federated search with Stack?
We're sort of doing federated search and stack. So each of these data source services, they get a stack. You know, they implement the Stack API. They'll then say, am I supposed to search locally or am I supposed to search remotely? Because they're different use cases and we need to know which one it is you want. And then it'll query the local one or it'll query the remote one. But you know, Stack has this recursive query thing in it, at least as I understand it. But one of the problems is like PG Stack doesn't have multiple catalogs and it doesn't have hierarchies. So we use PG Stack for now, but we find it limiting that way. So we'll have to work out what we want to do about that.
One thing we've certainly noticed with a lot of the provider Stack catalogs is that there's quite a lot of variability
Yep.
in implementation.
Yep.
I'm not just talking about extensions, I'm talking about different interpretations of the endpoints, the APIs,
Mm-hmm.
the structure. Might be something you identify as well, but I'd be keen to get your thoughts on that at some point.
That's why we do this. Because each one of these has custom logic for whatever the difference is. You know, maybe they have the filter extension and some do and some don't. So if you have a SQL 2 filter that comes in and like, I don't remember, Copernicus doesn't have filter extension. I don't remember which one doesn't. And you go, okay, great. I don't have the filter extension, so now I need to use, you know, their more basic search language, the one that's built into Stack, but I need to get more data back, and then I need to filter it in that middle step.
It's interesting, you take, for example, iSize Stack interface, right?
Yeah.
Their items have 160 attribute
Yep.
extension on it.
Yep.
That includes satellite state vector.
Yep.
There's some interesting interpretations of how to extend Stack. I'm yet to see two observation providers that have implemented it the same way.
Right, and that just goes back to the original Orbital problem that Stack is great, but all the metadata is different. So we still have that problem. And you know, there's some standardization, which is great. The more the better.
Even the API interfaces, they can be very different in some cases.
Yep.
Yeah, it's federated Stack is something we should look at, but it's very hard to implement. We
So-
spent 3 months trying to do it. It was quite tough.
I'll come chat with you. I'd like to know more. One of the things we punt a bit on this is when you have an algorithm or an analysis that you add to Terrascope, it's trained against some data source. So a lot of this we push back to the algorithm implementer because an algorithm is not going to run on Maxar and Planet. I mean, they sort of kind of barely can, but they don't do that well. So you know you've trained your algorithm against SkySat. And so since you know you're trained against algorithm against SkySat, you know what metadata you're going to get from SkySat. And so part of this we just say it's the implementer's problem for now.
Curious to know about, say, geolocation data support for operational use case like disaster response.
Mm-hmm.
You guys support that right now, or are there any plans to support say, streaming geolocation data for disaster response?
So not for disaster response, but for the one with the GPS spoofing and jamming, the sooner you know about it, the better, because I guess in theory it could prevent a disaster. So we're working towards that. So nothing's real time, but we do get data from some, it really depends on the provider. Some providers give you data every 10 minutes, some are every hour, some are every day. And so it's provider specific. And on the satellite imagery, it's very provider specific. If you task how long it actually takes you to get something back, because it depends on so many variables, of course. So this will never be a real-time system, but we'll try to make it as close to real-time as possible. So if we get data and it's 10 minutes in, then we can process this as it comes in, and then if some analysis flags something that needs to be done, then we can see that. But that's still incipient stages.
Okay, yep, sounds good, thank you.
Yep. Okay, thank you. Nope, sorry, oh, another question.
We have a little bit of buffer time, so
Okay.
I'd ask one more question. So
Sure.
you said you're using PG Stack.
Yep.
And you're using cloud-optimized GeoTIFFs.
Yep.
You've probably heard of T-Tyler PG Stack.
Yep.
And I'm just wondering if there's a reason why you wouldn't use it.
So one of the reasons we do use we actually have been playing with T-Tyler. We've been playing with it. So the issue that with T-Tyler is one, I don't think, but we're investigating it, I don't think it deals with this, which is this. I don't think it deals with this, right? So that's one issue. And the other thing is, if you're requesting a whole bunch of tiles and you're dynamically generating them, how fast can it be done? So we've run some experiments. You know, if it's on disk, from S3, it's super fast. But you know, if you need to go serve X number of tiles to X number of users, is that actually fast enough? I'm not actually convinced it is. But what I've seen from our numbers so far, it's great when you can use it, but it's probably not what you can use all the time. But I think that changes over time. It gets faster, and we can see if we can optimize it. But the reason for cogs is T-Tyler is really not going to work without the cogs. So they kind of go together. More questions? Great, thank you.